When we look up at the night sky, we see a mostly dark, quiet void. It feels peaceful, punctuated only by the faint twinkling of stars in the visible night spectrum. But moving beyond the visible spectrum exposes a chaotic landscape of pulsating neutron stars and glowing planetary echoes. This is the universe through radio frequencies, an environment our eyes were never designed to see. The universe constantly broadcasts its history across these long wavelengths. Humanity's goal is no longer just observing the cosmos, but learning how to listen to it. Optical telescopes are easily blinded by physical barriers. Thick planetary atmospheres and clouds of cosmic dust act as a visual veil, blocking the light we rely on to understand our neighbors. The planet Venus is the clearest example. Its surface is permanently hidden beneath dense clouds of lethal acid rain that completely block observations. Astronomers bypass this barrier using active radar. By transmitting radio waves that slice through the Venusian clouds, they were able to map the surface and discover that the planet's rotation is actually retrograde. Radio observations also found ancient water ice preserved in the permanently shadowed craters of Mercury. Because sunlight never reaches these crater floors, they remain invisible to optical light, but radio waves detected the signature of ice decades before a robotic probe arrived to confirm. Radio astronomy is the primary tool we have to look past these physical and atmospheric barriers, whether they are on the next planet over or at the edge of space. Looking toward the furthest reaches of the universe reveals a temporal barrier, a hazy fog of neutral hydrogen that filled the cosmos for hundreds of millions of years. To see through this fog, astronomers focus on the 21-centimeter line. This is a specific frequency emitted by neutral hydrogen, and it serves as the radio signature of the early universe. Tuning into this frequency allows astronomers to observe the epoch of reionization. This 3D map shows how the 21-centimeter signal traces the intricate web-like distribution of dark matter and hydrogen as the first structures in the universe formed. Because this radio signature passes through the cosmic fog, it shows exactly how the first stars ignited and transformed the surrounding gas. Mapping this signal is the only way to uncover the foundational architecture of the cosmos from a time before visible light could even travel through space. Distance presents another barrier. Imaging objects as compact as supermassive black holes requires a level of resolution that no single telescope on Earth can provide. The engineering solution was to create a globe-spanning network of synchronized radio dishes. By timing their observations perfectly, they can function together as one virtual instrument. This was the strategy behind the Event Horizon telescope. By combining data from receivers across 4 continents, astronomers effectively turned the entire planet into a massive radio antenna. This is the result of that global coordination, the first ever image of the supermassive black hole at the center of galaxy M87, visible only through its radio frequency silhouette. As the distances we study become impossibly vast, our ability to observe them depends on scaling our technology to match the scale of the cosmos. This is the future site of the Square Kilometre Array, or SKA. Currently under construction in South Africa and Australia, it will be the largest radio telescope ever built. The SKA will survey the sky 10,000 times faster than our current arrays, generating a staggering 700 petabytes of data every year. This creates a massive computational hurdle. As this flowchart of the Science Data Processor shows, the volume of data is so high that it cannot realistically be stored. It requires real-time supercomputing just to filter the incoming signals. These specialized pipelines sort through the massive data streams instantly. This real-time analysis allows the system to catch transient astronomical events as they happen, before the data is discarded. The same technology used to isolate black hole jets is now sensitive enough to catch the faintest anomalous signals from across the galaxy. This listening power equips us to finally hear the answers we've been seeking for decades. The universe is echoing. We have finally developed the technology to listen.